Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I'm pleased to welcome Han. I'm not going to try to pronounce your first name, Han. So Han is a distinguished scientist and managing director. I'm not on here. Let me start over. So Han is a distinguished scientist and managing director of MSR Asia. Han joined MSR in 1995 from Apple Computer. He received his PhD in computer science from Carnegie Mellon. So Han.
Thanks, Rich. So it's a great honor to be here on behalf of the entire MSI to actually tell you what Rick and the China Rick and MSI and how this all started, and then thanks to Ed already planned for my talking about MSIA. And I think so. Before I actually go to my presentation, in Asia we have a tradition. Every time we do some event, we must take picture. And I think because this is the real proof that things really happen. And particularly for Rick, we can show to Terry and kids every year. Rick did come to China and Asia. So starting our opening in '98, and also we do, Ed mentioned, we actually engage with the academic community, just like what Rick set up the MSR, and I think we actually also responsible to bring the top research or scientists, professor to China. So people, really, including Ed, you can see many people in the picture. Really thanks to Rick, all this academic exchange, and for their first trip to China, it's all because of our event, because of Rick. So you will see all the familiar people, including many people in this room. So every year, 2005, 2006, and we start doing this bigger, larger than life photo, right? Okay, here's Ed. Okay, 2007, 2008, and our 10th anniversary, and so we all look the same 10 years ago. 2009, still in our old building. 2010, I remember the Shanghai Expo, and people, we have certainly quite a trip there. And last year. Okay. All right. The picture time. So it's all started because of Rick, and we certainly achieved quite some feat during the last 13 years. And I try to use the next 15 minutes to tell you how did it all happen. So start with actually Rick's PhD thesis. Okay, you will know why. So Rick's thesis is about system for interpreting the moving light display, 2D, no depth. Okay, that now you have connect and actually have the depth. Really just only 2D, just start. Just basically just start. And I think even for human being, I don't think many people can actually really interpret this. And I think Rick take the challenge to really start doing tracking, understanding, and on this moving light. And I think it's really a huge inspiration. Like even back in 1979, 1980, it's possible to reconstruct the human motion based just on this very limited data. And of course the non-rigid human body, which we sort of movable, but with some physical constraint, you cannot bend yourself too much, and because human body are sort of deformable to some degree. And I think if people know about MSIA, we first make our name in the multimedia area, particularly in computer vision and computer graphics. And I think Rick's thesis really inspired many work we have on motion synthesis, analysis, tracking, capturing, reconstructing. And I will just show you some of the same sort of the significant paper we published along the line, particularly in the early day. And I think this is the paper in 2002, and actually Harry, my predecessor, is one of the co-authors. This is kind of typical analysis and synthesis. we try to find every motion. It's a linear dynamics system combination of some short-term pattern, and we call that textual. And then so by doing this analysis, any motion sequence like dancing, you can be really a dynamic combination of all this textual. And then we actually, believe it or not, we actually using this information in today's Bing video search. When you do the video thumbnail, we actually use some of this technology today. So I think that's certainly one, the work inspired by Rick Scissors. And then the second one is the paper we published 2 years ago. And so so in the graphics, you are trying to reconstruct to represent some motion in animation or whatever, the scenario. And then you can now recall every possible motion. But at the same time, trying to apply physics to actually on any action is also clearly today is impossible. So this we take an approach. We actually take a video recording on some basic motion. Then you apply some local physics to actually change to, for instance, on the left-hand side you see the recording motion, and then now if you actually fall through a step, we kind of apply some local physics. It's actually not. It's strictly speaking, it's not real physics, but it's all computer graphics. It's about you apply enough for people's eye. It's actually like that sequence on your right. It's actually what we computer generated. And then the next, the one on the bottom is like you apply that sequence on two robot and with some kind of deviation. So that's another work which was inspired by Rick Scissors. Then last year we published a pretty significant paper in SIGGRAPH, which is for a long while, people, I mean, if you are in movie industry, the moving light, like the Rick Scissors, is really like the body of moving lights. I mean, like what you see on the left-hand side. You do, that's called motion cap. You basically just put the dot on the body or face and trying to record so you can do in reconstruction. The problem with that is that typically you actually trade off spatial with spatial versus like time resolution. So if you have a very good motion, you actually lose the spatial resolution. So the paper is the first attempt to actually using a laser scan, but laser scan you can only take the static image. So we kind of combine both by find some we call kernel phase scan, and that gives you vivid the laser capture of the face. Then in between, we use in the motion cap start to do interpolation. So this way, we can generate something like this. So you can see the scene on your right hand side. So that's what we actually be able to generate. And then on the tracking, again before connect, you don't have the depth. This work we actually done before the connect for the Microsoft LiveCam 5 years ago. And then the face is actually just like what Rick said, the moving light display. So it's non-rigid, it's deformable, it's changeable, but with some constraint. So we use the important feature in the face, like eyes, like nose, like mouth, so to as a cue, and then help us to do the real-time face tracking. So this way we can, of course, we can do connect avatar, which many of you know today. And actually today in the Microsoft O webcam, you can actually like put some really spatial effect, wear a hat or wear glasses or make your nose bigger or smaller, because we can do this real-time tracking. So that's on multimedia. I say we sort of make our name. So in 2004, there's a lot of the press, also the book about MSRA. And in 2004, one significant event in terms of being recognized or in the PR front, the technology review called us the hardest computer lab. And I think which is basically it's a great tribute to how difficult to do the world-class lab outside US, particularly in China, and how we do it. It's a good compliment to us. And that summer, actually, we literally it's the world's hottest computer lab because the air conditioning is broken. So I think that it's right timing. And so that's we. However, we all know the Rick. Actually, after his sister's war, he came to CMU, become a top system and networking professor. So Microsoft also, I would argue, Microsoft is basically a system and networking company because we are a platform company, infrastructure company, create a platform for people to build all kinds of system and software. So we actually told out the always regard until we build a world-class system and networking team and the project portfolio, we are not really world-class yet, particularly on the RIC. So we over the last few years, actually, we take us more than 10 years to really build a strong system and networking portfolio and team, mostly because of the talent. And as several people mentioned already, the best way to really start is really the talent. But unfortunately, there are fewer top system and networking researchers, Chinese researchers out there for us to actually recruit. Therefore, we need to mostly build ourselves and also gradually. It does take longer than we thought. But I'm happy to tell you now we actually built a great system and networking portfolio and team. And I think here is some of the work we have done in the last couple of years. The first one is on the SORA. It's a software radio platform. Software radio. Actually this one is kind of similar to Mark in the sense, inspired by Mark, is like it would be wonderful to actually do all this in software except the radio. Like we all know the wireless, we need a lot of chips, the ASIC chips in doing all this kind of DSP. Similar to Mark in a sense, can we actually put so many features, microkernel, multiprocessor, all this stuff in the very slim and also a portable OS? And I think a lot of people probably will say no, that cannot be done until you really do it. So I think the team really take this challenge to implement a solution which is you basically has a PCI card with basically just a basic radio and all the heavy lifting DSP and other stuff which is done in software. And I think we actually won several base paper award and also being adopted by 40 plus university make a quite impact in the wireless area. And then the other direction is the data center networking. And I think I'll just quickly talk to you a few work there. As you know, now we move to the cloud era. So I think the data center network it's ever increasing important. And I think one of the things we do is the BQ, which you give a different topology to give a direct link between any two server rack. And I think that's we're one of the first school to publish paper in this area. The other one, we got the NSDI 2011 base paper award. It's the server switch. Yes. Okay. And then this is again using the commodity hardware and the ASIC to actually allow people to do flexible packet forwarding and etc. And then PMesh, the stuff we do with OSD to actually have monitoring and diagnosis stuff to actually knowing what happened in the network stack in the service. And then in the distributed stuff, which we have the Modest, which we actually work with the several service in the cloud service on using the model checking and other technology to help for testing in the distributed system from. And Cloud Meter is also the other similar one, but this is on the system log. And Tiger, which is the last one I'm going to talk about, which we also carefully choose the project code name. If you carefully choose the project code name, you already halfway success. So we recycle the Tiger project. This is basically this is new index architecture for bin. and 2 level, so we can actually put a smaller index in on the RAM and put a bigger index on the SSD, take advantage of SSD, so we can actually create a 100% performance gain. So now, really the last slide. I think so from all this, I think here's our take, like our experience of how to build a world-class research lab. You start with a leader like Rick, and then you take all the technical inspiration you can from him in this particular case, we already on multimedia, computer vision, graphics, system and networking, and then the most important thing I would say, I extract the research methodology and value already pointed out by many people. The to advance state-of-the-art principle come first, and then to contribute to a company to not just the technology transfer, also build this technical reservoir for the company, and then the system approach, the can-do approach, which this is why we typically say, well, no matter how good the theory is, we want people to actually just try to build a system, and that's also important. Well, on the risk-taking part, the other side always say is fail fast. You try something, if it doesn't work, you quickly switch to trying to build something else. And then finally, the research is it's more about people, not technology. Again, echoed by many other people. Okay, thanks.
Okay, so I hope the title is interesting. Let's see, should I do this USB thing? No, I'll stand here. You can see me, right? I can see you. Well, the history of India Lab goes back a couple of years before it started. I started pitching it, and then took a while to convince Dan and Rick. But interestingly, the place, the time where it was finally decided was in the 2004 TAB meeting, which actually might have been held in one of these rooms during TechFest. And we had Richard Newton at that time as a member of the TAB, and Andy Van Dam, and of course Raj is here, and Ed is still here. And together with John Nodlinger and Maitreyi Ganapathy, names some of you may remember, may not remember, we put together a presentation. I still believe it's the picture of Taj Mahal that got Rick to decide to set up a lab in India. It can't be anything else. And he said, well, after the talk, I went to Dan and I said, what do you think? And Dan said, well, I don't think Rick has enough money in the budget this year. I said, oh, well, another year. So then I went to Rick, and Rick said, well, if you're going to keep it to under $2.5 million for the first year, I may be able to do something. So that got me working. I took Dan to India on a whirlwind 5-day trip. He didn't get sick because he told me that I didn't give enough time for him to get sick because he kept going from one city to another. And then I came back to Rick. So what should I do? He said, you have to do 4 things in order to get ready to set up a lab. First thing was people. He said you have to have people. So I recruited Sean and Kentaro, and as you can see appropriately, I also dressed them up in Indian clothes. Kentaro, of course, is not working at Microsoft anymore. And Sean now is settled in India, by the way. He wears these kind of clothes every day, as far as I can tell. An agenda, of course, this is our initial presentation. I won't bother reading it, but just to show that there was an agenda. We had 4 research areas: sensor networks, multilingual system, digital geographics, and technology for emerging markets, 2 of which we, in fact, no longer do. But that's the nature of mission goals. But the mission goals is very similar to the MSR one, so I just borrowed them from Rick. And a place. Sean and I went around looking for a place and looking for a place and looking for a place and looking for a place. And 29 buildings later, we didn't find this. We found a shell which wasn't built up. Then it got built up within a year, and we were there until recently, as many of you would know. And then the last thing, of course, he said is that we have to have a PR. So, well, this is was not the announcement, but this was by our facilities manager in India, who thought that this was the most appropriate, but this was really the announcement. We had an article, and so we actually had a lot of PR. We had an intent to set up the lab announced in December 2004, and then an inauguration of the lab in January 2005, and then inauguration of the building in October 2005. And so we were just looking for events to do, and we kept. This is the the speech from the inauguration. This was the Minister for Science and Technology. Oh, okay, I don't have audio, so I won't show this now because I didn't connect up to the audio. Some other time if you want. This was actually the plaque. So, one thing, of course, we do in countries like India is to engage with the senior-most government officials. It's a good way to sell both sides. I convince, my management that we are important. I convince the government of India that we are very serious. So we take Rick around. The Minister for Science and Technology, Mr. Kapil Sibal, was the one who inaugurated the lab. Now, we understand right after this, he got promoted to a cabinet level minister, clearly because of setting up MSR India. Couldn't be any other reason. And of course, within a year, we had some crisis, and I don't know if Rick remembers this. One of the things that happens in India is that people are very sensitive as more to Bollywood actors than to politicians. So it just so happened that we were literally within a stone's throw of a famous Bollywood actor's house. I mean, and so when he died, and he died, by natural causes, there was a huge procession, and people coming to see him, and they went for miles, and there wasn't enough time, and so people were getting upset. So as a part of time pass, they started throwing stones at all the glass building that was along the way, and we happened to be right there, and we lost all our windows. We got to replace them, and it didn't seem much at all. Frankly, it's just the kind of thing that happens routinely, and it's just kind of thing that you deal with as you go along. So this is that's India. And of course, we put garlands to minister when they come to inaugurate your building, and they're heavier than, can't be possibly heavier than the ministers, but might be. And Rick got to learn Indian traditions such as lighting a lamp. And of course, we took him to famous temples and all this kind of stuff. Now, one thing about Rick, and I'm going to ask Terry this, I've told him every year, you have to bring your family and do some sightseeing. And every year, he says, okay, so next year, I think we expect all of you to come. The horses in India are nothing compared to anywhere else, but don't come for that. But you can ride camels. I mean, that's actually a fun thing to do. So that may be the reason to come. We have a very social culture, as most of you know. And this was from our 5th anniversary party. And I think given that this seems to be the day when people are taking pot shots at Christian, I thought I should put this up. I do have a picture of the hotel person asking Christian, to politely to get down from the table so he wouldn't break. So Rick didn't come to this party. I mean, he usually didn't stay for the parties because he gets tired and all that. Next morning, I was sitting next to him. He was giving a talk at, I think, some Women in Computer Science Forum. And I'm, tired. I'm still not over from the party. And I sit next to him. So he said, I heard you had a nice party yesterday. I said, yeah. Rick, I think, sometimes I worry that we'll get a reputation for being a partying lab. He looks at me and says, Anandan, it's not the lab, it's you. The lab is just... I said, then if I still have the job after 5 years, when my boss says this, I don't think I have a problem. And this is from the next year where we decided to have a slightly more modest drumming sort of thing. And there is Rick, you can see him, happily enjoying drumming, surrounded by some very senior people of some distinguished nature. So I'm not going to get too serious about anything, but I should say one thing about working for Rick. And I think most of you have said this in some form or the other. I think you get unlimited freedom. He doesn't tell you what to do. In fact, if you go ask him what to do, he'll send you back to find out what you want to do and then come back. I remember in the early days, we had a crisis where some of our friends were not convinced that we should be a separate business entity or some such issue. And I had a certain idea. I talked to Rick. Rick said, what do you think we should do? He said, what do you want to do? I said, what do you think I should do? He said, well, you tell me what you want to do. I said, how do I figure out? He said, well, you analyze the problem, figure out what you want to do. You come and tell me. If you're right, I'll say it's fine. If you're wrong, then he didn't finish it. I figured you'd fire me, but turned out to be right. But then once you tell him and he agrees, he supports you all the way. So when other people try to detract from it, I remember he sent me an email saying, so-and-so sent me this email. I think they're trying to do an end run around you. What you want me to do? And then he sticks by you. I think that's really great. Total ownership and looks for results. And I think this is one of the maxims I learned a long time ago about how to deal with your manager. Don't go to him with problems. Go with solutions. And that's absolutely true with Rick. Well, thank you, Rick, for 7 years of wonderful time in India. And I should also thank Dan, actually. He was quite instrumental in helping us. And I think this is where I'm looking at in the future.
All right. Thank you, Anandan. So next we have Jennifer and Christian. I think they'll get a chance to rebut some of this fire they've been taking.
Well, I'm just waiting for Nathan's FestSchrift. I shouldn't take this out on Rick.
Oh, yeah, be careful.
There we go. Okay.
All right, so while they're setting up,
While we are setting
I
up,
will take the chance to introduce them. So Jennifer Chase is a distinguished scientist and managing director, also founding managing director of MSR New England. Jennifer joined MSR with Christian in 1997 when they co-founded the Theory Group. Christian is currently deputy managing director of our MSR New England lab. And they are going to jointly talk, and I'm not quite sure how they're splitting up their topic, but they'll do that. I guess that's the way they work.
that's the way we work.
Right.
Can people hear us?
Okay, can you guys hear me? Good. I have the clipper set up, I think.
Jennifer, you're not loud. You lost me. I'm not loud?
Impossible.
That's interesting.
Okay. Can people hear me now? Good.
Okay, so I'm the German husband, in case you don't know who I am. And one thing
Dances on tables.
right. So when I actually came to interview here, what I realized after roughly 1 minute with Nathan is A, he was a little bit afraid of me. And B, he really was trying, he was not judging any of my qualifications. The only thing is he wanted to make sure I'm not like the previous husband. And I think I passed. Okay, and I think Jennifer will have more rebuttals, so if you want to.
I wasn't planning on rebutting. So how do we get this? Let's see.
You want the clicker?
No. I have to do this PC8. Is that?
Which PC are you connected to?
I think I'm connected to PC8, just like a mathematician, yes. Here, I'll let a systems guy. Do it. You have to give me the clicker, too. Okay. So, you see, I'm no longer wearing dog collars. Okay. And great. And so I have all kinds of memories of coming here and being recruited in 1996, and then trying to figure out in 1997 with Linda Stone and Rick and Dan how we were going to convince Christian that Seattle wasn't, the dark side of the world.
So I said to Jennifer look, Seattle can't really be that nice and exciting a city because otherwise everywhere in Europe we would have heard about it, and we haven't. And so then Linda sort of was recruited to solve that problem.
To help us convince Christian. So,
but actually the person who really convinced me was Rick, who actually managed to convince me that Microsoft research is not like some of these. You see, I'm from Germany, and you go do an internship in some industrial labs there. It's structured, okay? And so I was very skeptical about going to Microsoft. That sounded really worse. And Rick was really the one who convinced me that this is a gorgeous place to be. Thank you so much, because we are both very happy still here.
And I think we're happy with our new lab. I know most of the stories that you've been hearing in this session are about how these new labs started and got off the ground. Most of our talk will really be about research and about research freedom, the freedom to do crazy things or things that don't have obvious connections to Microsoft. I did want to give one anecdote about pitching the New England lab to Rick. I went in and I had a meeting with him, and I pitched that maybe we should open a lab in Cambridge and it should focus on the intersection of computer science with the social sciences. And Rick took a minute and he looked at me and he said, "That's not the stupidest idea I've ever heard." Which, I don't know, Terry, whether you've gotten that occasionally. That's not the stupidest idea I've ever heard. Rick mentioned to me that I should go talk to Butler, who was our one person who was sitting in Cambridge. So I did. I went and I told Butler this, what I thought was a characteristic Rick story. And Butler said, "That doesn't make any sense." And I said, "Why?" And Butler said, "Well, because 10 years ago, I pitched to Rick that we should open a lab in Cambridge, and Rick said to me, 'That's the stupidest idea I've ever heard.'" So that is my story on forming the lab. Somehow out of my mouth was a little bit better than out of Butler's mouth, which tells you that Rick has a strange utility function, I think. Anyway, what I want to talk about is research freedom. I know that there has been abstract talk about research freedom, but for me and Christian, we have continued to do research while being lab directors. As Nathan mentioned, we did really bizarre things relative to computer science. We did phase transitions, and we somehow have gotten from there to things which might be a little more useful and then went beyond useful to useless again for Microsoft. So even though there are more useful things to come, hopefully. So I'll tell you a little bit about that. So I'll tell you about phase transitions. Christian will tell you the meat of the story with the algorithms and the Steiner tree. And then I'll talk about the cancer genomics work that we're doing. So phase transitions, water to ice, water to steam, that kind of thing. We know now that phase transitions can also happen in combinatorial optimization problems. So this was, Nathan came to Rick and to Dan and said, I know this woman who is working on phase transitions and combinatorial optimization problems. Doesn't that sound relevant, right? And I'm sure he got that look. Just that look. Okay. So what are constraint satisfaction problems? For those of you who know them, you'll understand this. For those of you who don't, if there are any of you, then you won't. But anyway, they're just resources and constraints. There are constraints among these resources. The resources are variables or literals. You could do this randomly. You could say, oh, I've got n variables or n resources. I've got m constraints. I'll draw the constraints randomly and put them together. What are the odds that when I do this, it's going to be possible to find a satisfying assignment? So, if there are lots of resources and very few constraints, then, not surprisingly, you can satisfy it. And if there are lots of constraints and very few resources, you can't satisfy it. And what's kind of interesting is that there's a sharp transition. So it falls off very quickly, and it looks a lot like a phase transition. And from a computational point of view, what's interesting is that the difficulty of the computation is maximized near the phase transition. So in studying the phase transition, you learn something about the structure that is making this problem hard to solve. It's a critically constrained problem. And so we were looking at these things in our first few years at Microsoft, and there were other people also looking at these things. And in so doing, in using physics, which sounds like a bizarre thing to do to study computer science problems, we gained some insight into how these problems work and how to solve them a lot more efficiently. So Christian will talk about that.
Okay, so I will first tell you a little bit how these strange algorithms work. Sort of Nathan would love to listen to it because it's done by physicists and they know all these things much better than us mathematicians or you computer scientists. But so what were these algorithms the physicists developed? The physicist will write an E somewhere for energy, obviously. So you have this energy, which is a number of unsatisfied clauses. You put a probability distribution and you try to solve that. And in particular, if you would find the maximum, then you would find the satisfying assignment if there are some, and otherwise the best you can do. And what is really important here is something called a factor graph, which consists of the, how do I get this thing to make here? The nodes, which are the variables Jennifer had, and then M, where these constraints or clauses on the other side, and you link them whenever a variable is constrained by the constraint. And this graph is sort of a nice little graph, and then belief propagation is something which passes messages along these edges here back and forth and magically solves for this formula up here. Okay, so I just show it here to you. So you have some, don't really worry what it is, you have some probability distributions where the variable knows something about the word and tells a constraint, and the other way around, and you pass them along where this variable collects all the messages and calculates a little bit, sends another message, and it's very nice because it's actually highly parallelizable. So there are actually people in Microsoft who try to put that into as one of the applications of multicores, because in contrast to other constraint solvers, this is highly parallelizable. And now we come sort of to to our work, and I have to somehow relate that to Rick. So here's my very lame attempt. So assume you have 3 planets which are far away, each 1 light year. Okay, and you need to get something to 2 of the others. Okay, let's say you sit sort of on the one on the left here. I really have difficulties with on this guy, and you want to send it to both these. What do? Well, you ask your mathematician friends and say, you need a spanning tree. So you find this minimum tree to connect that, and here it's very clear you have not much choices. It's 2 light years, okay? But now it turns out actually you forget you actually have the Enterprise somewhere, okay? So here in the middle you park the Starship Enterprise. And since I was signing a release form, I had to remove the picture of the Enterprise and put here a dot, because otherwise I get into trouble with Rick for copyright violations. So it was much more fun before, but anyhow, we now have it like this. And now we can see what do you have to do. Well, obviously you need more fuel because you have more places to go to. Well, that's actually not true, because now you can go here, then sort of start 2 little ships to these, and if you calculate the fuel you need, it's actually less. So that is called, so the Starship here is actually called a Steiner node, and the Steiner node actually reduces the cost. So this is, what does it have to do with MSR and Microsoft? Well, it turns out you have to go on networks. Okay, let's say you have some computer network, you have some graph mathematical, you have something called terminals, which are places you want to connect with each other, and you have costs. And then what you find is a minimum tree connecting all this stuff with minimizing this cost. So in this example, you see you have to add 3 extra nodes. You want to add not too many because that otherwise will have a huge cost. And these extra nodes are called Steiner nodes. And Jennifer will tell you what Steiner nodes have to do with biology, but I will tell you what they have to do with computers. So there are many applications in networking. The simplest you can all understand is sort of broadcast, right? One of the terminals is my server, all the others are the terminals, and you want to add as little network to it because that cost. And so now there are variants on it which are important for biology. You don't necessarily serve all customers, only which give you huge prices. So you collect a price for each terminal you include. You have a slight variation, which Jennifer will soon sort of talk about. And now you want to use these new algorithms. And this sounds very nice. You try to write down the factor graph, and it's a little problem. So the problem is that you have this global connectivity constraint. You want to connect everybody, which is a constraint containing everybody, which is not very parallelizable anymore, and it's actually also just doesn't work. So what we did, it's a few postdocs, and Ricardo was one of the original inventors of these algorithms. We patented in sort of 2008, I think. We came up with a new representation which makes this local. It's sort of the details are not that important. And once you have that, it turns out that all constraints are local. We can use sort of belief propagation as before with messages back and forth on the factor graph. And it turns out it works really nice. We tested it on benchmarks, and in contrast to standard algorithms which are LP-based, this works sort of a factor 1,000 better so in time, which means there are a lot of problems you now can do, which before you couldn't. And among those, Jennifer will tell you a little bit.
I'll give you 5 minutes of biological problems that we've been doing with this. Okay, so there are DNA chips, and for each experiment, for each experimental condition, you get a chip which lights up for the proteins that are differentially expressed, that are expressed differently from what they are in background, either much more or much less. And you figure they lie on some pathway that has something to do with the process that you're looking at. But there are some proteins that may be really important for the pathway, but they work in their background amount. So they're not upregulated or downregulated. So how do you know that these proteins have something to do with this? And so we treat it as a Steiner tree problem. What we do is we say the ones that are upregulated or downregulated are the terminals, the things that we attach prizes to. We have costs, which are which come from knowledge of whether protein I will interact with protein J, typically in that organism. And then the extra nodes that we insert we think of as proteins that are important to the pathway, but they're not up or down regulated. Okay? So we did this in yeast, and yeast is known to have 4,000 or 5,000 proteins, about 15,000 known protein interactions. When we did this, we took 56 different experiments. We got a tree for each one. We put them all together, and what we got was this network for the pheromone response pathway. There were two kinds of proteins, the ones that we had basically put in, and then the ones like the Starship Enterprise. Okay, so that causate is the protein that we didn't expect to be in there that was in there. Does that have anything to do with what's actually going on in yeast? So we begged and begged and begged, and we finally found some people who were willing to go in and knock out the corresponding gene, and the pheromone response pathway fell apart. So that was experimental proof. Okay, but who cares about yeast? We care about humans. Well, here is where it's really nice that we have a fast algorithm, because there are about 25,000 proteins, 230-odd thousand protein-protein interactions, and none of the LP methods work. We've talked to lots of biologists, and we've got some now finally who are able to use our methods for this. And we're doing work on the Cancer Genome Atlas, which is about 20 kinds of cancer. The NIH has put tons of money into this. It's its biggest project now, and people are looking at many different kinds of cancer. The first one that we started looking at was glioblastoma, which is a very deadly form of brain cancer. It's much more common in men than in women, about 4 to 1. It's what Ted Kennedy had. There are no good drug targets. And the Frankel Lab at MIT used our algorithm to construct trees for hundreds of glioblastoma patients, put them together. This is what they found. Now, it turns out that a lot of the things on the network they found have to do with known biology. But the things which are not red, which are white, didn't get any prize or penalty. And then the ones that are very large are the ones that are very central. So things that are very central, but we weren't putting in there to begin with. For example, this protein here. What is that protein? Okay? It's the estrogen receptor. So this is the first explanation of sex linkage in glioblastoma. And the experimental proof is that we put estrogen on glioblastoma cultures, and it seemed to kill the glioblastoma. And we're doing other things with Steiner Forest and blah, blah, blah. Anyway, but it's kind of cool that the same algorithm, to us it's kind of cool, that works for multicasting, also works for cancer genomics. And it's the kind of thing that Rick, if not encouraging us to do, he lets us do, because along the way we find many interesting things. So this is part of our journey, and thanks for your attention.
All right, thank you, Jennifer and Christian. So let me get Gordon up here. Here's the microphone. Turn that on. It's on. Is it on? Yep.
Oh, and I want to apologize for leaving. I broke a tooth, which means that I have to miss all the rest of the talk. It's not that I'm just a jerk who walks out after I speak. And I don't walk very well either, you might have noticed.
All right.
So I'm again the one left to dance on.
All right, so let me introduce Gordon while he's coming up. Gordon Bell is a principal researcher at MSR. As you heard earlier, he advised Nathan Mervold and helped to hire Rick Rashid. But for some reason, I'd like to hear this from Gordon himself, for some reason he did not actually join MSR himself until 1995. Gordon worked at Digital Equipment Corporation for many years, where among other things he designed the PDP-4 and the PDP-6 and led the development of the VAX mini computer that we heard about from Avi. So, thanks. Gordon.
Great. Yeah, in the written rift, I try to outline my side of the story, and I say substantially Nathan does a pretty good job of saying what it's like. I have it in my notebook, and I've got to say, well, the searching, at least the notes in my notebook are my typical way of decision making, of a table of people and some characteristics, and Rick was at the top. So he was really targeted in terms of a search. But we traveled around because it was fun traveling with Nathan, talking to all these people and rejecting them. I really need to start by congratulating Rick in terms of what MSR is turning out to be on Rick's, I would say, his second trimester, and I'll talk about his third trimester of his life later. But anyway, he's 2/3. He has a problem of what's he going to do for his real encore. I'm really, frankly, honored to be part of his organization and to congratulate him on the way it's turned out to be, along with Nathan. The other thing is, I think as on this third trimester, I hope he doesn't turn into a steer roper or endurance rider. He's got a lot of experience there, and I think part of the Microsoft environment, as far as I can see, really turns out to be good training ground for a barrel racer, and that exhausts my understanding of equine analogies. I think in the spirit of what we've all heard, it's no surprise that, in fact, he ended up recruiting and marrying Terry, who he could delegate, and now he has become a horse rancher. Anyway, so one of my fondest memories of the early TAB was meeting with Bill Gates, and the TAB. In the early TAB, we were trying to convince Bill that this thing called the internet was really real, and that Microsoft probably couldn't dominate it and control all the standards and everything. And then eventually the market, by 1995, the market turned out to agree with him. And so Microsoft got with the program at that point. The other thing that happened with the TAB was that it did a little bit of off-premise betting that several of us profited from. We made 3 bets or predictions in '93, and the first one was by 1996, video on demand would have 500,000 subscribers. 2, in 2003, cars that drive themselves would be sold, and 3, AI would be considered more important than the transistor. Prediction, of course, is hard here. Now, video appeared in 2009. It turns out I lost a bet, so I can say that's when I think it appeared. And so our 3-year close-in prediction turned out to be 15 years. This was off by a factor of 5. Let me define this factor as RFF, or it's called the Raj fantasy factor. We hear about factors here, and so I want to really mark this one. And now Raj was in good company here, because Tiger, I hear the story about Tiger today, and when it was done and when it actually appeared. Now, cars that drive themselves may come in by 2023, so let's make that a fantasy factor of only 3. Now, on the AI bet, it's your call. I'd put that maybe at infinity, but anyway, we'll see if that ever comes to pass. It only will when we forget that there's something called a transistor. Okay, now the part that I completely blew, because I was making these promises about to Rick about what it's a letter that I wrote. I'll say it's probably one of my best letters. Nathan refers to it. I didn't remember that he wrote a letter. I spent all weekend writing a letter, and he's right. It was a very hard sell. It was like you just can't, no is not an acceptable answer here. And so I sent it to him, addressed to him and his family, and said, basically you're going to do this. Or here's why you have to do it. But anyway, it was obviously my part was successful in that. Now, in that letter, one of the other things, other than I said, the pay's probably okay too, is that it's going to be really easy to transfer research into products because you're so close there. You'll be in the same area, and so there should be no problem in that. And so you have a maximal impact in the world by having all these products come out. Now, when Jim Gray started the San Francisco lab, who I also think I have a role in recruiting, and then Jim talked with me, it was about, we really felt strongly about that we wanted to do essentially advanced development, stuff that would immediately or could go in and be out there so that people could use it, and then we would know and it would be a practical thing that people could use. Jim's Terra server went through so in fact it was an AD lab. Jim's Terra server went through the technology transfer all right. It became Google Earth. And then several years before, adopted as Microsoft's Virtual Earth. And somehow I think there's something about that, which is there's a DNA within Microsoft of you first need to get a competitor out there so we can come from behind. This almost seems to be an instilled part of the DNA. We need to compete with somebody. If you have something really new, there are a few exceptions. It's very difficult to find somebody to compete with. So in our own stuff, I'm always looking for competitors. In our own case, the My Life Bits has really been a template for over 20 startups, including Evernote, that claim us as their research arm. And every couple of weeks or so, a new company engaged in life logging visits me for advice and occasional for sale. But I still expect Apple's iLife is going to have to evolve to such a state that it will become a competitive threat, and then we will respond and do very well with it. And whether something like this, we seem to want to reject or accept something, seems to be a function of the pain, the competition, politics, and overall just luck. So I watch my colleagues at our lab in Silicon Valley trying to birth Dryad Link, and the corresponding pain of friends in Australia who are trying to or would like to use it. I think we all should wonder a little bit too whether the distributed environment that came from Xerox PARC that's always quoted could actually come from Microsoft. If so, would the transfer have the same fate as the Xerox transfer or lack thereof? What about Siri or Watson? Could those things have come, or how do they come from a lab? Or do we care because the product demands are not there yet? What to me is exciting, probably our most recent and valuable transfer certainly is the Connect, because it truly is something that it took the research to make it work. Certainly you have people there that had a product vision. It was clear what they wanted to do, but in fact, this is a case of not having the technology to do it, and that was the critical link that made it work nicely with research. Two products I use, by the way, are SenseCam and Collage. Both came from Cambridge, and Gadgeteer is something I'd like to use if I had time. In SenseCam's case, the Cambridge camera was superior to the commercial one that was transferred. So is it necessary to carry our research as far away from Redmond as possible to have it a product? So this is a direct product to market transfer as a product as an internal transfer, and it's something I hope we'll continue to consider as XT has done in his case. By the way, an example of this strategy is the fact that Dave Cutler, who was referred to earlier, is at Microsoft. In 1982, when Dave, who was working for me at Digital, was in his, as he often does, gets a little bit perturbed, and as a manager, I knew how to deal with him. Basically, give him anything he wants. I said, "Okay, Dave, you don't like it here with all these people. You know, this bureaucracy. We've got all these people. Go anywhere you want. Do anything you want to do. Take anybody with you want." And he chose Bellevue, and that's why Dave pretty much is here. I think that's why we've got these remote labs such as Egypt and India that I really expect great things from. Now about your next trimester, certainly within 20 years, there's going to be machine classes out there that are in the order of trillions of computers. That is, there will be a platform built with that. And so my law of birth and death of computer classes allows me to certainly explain the 60-year path. And I think your next 20 years at the time when the computer itself disappears, because we can clearly see that by that time all of at least the electronics part of today's computers will be no more than a millimeter cube, if that, including the battery probably. Anyway, in the paper I mention of several potential platforms that will come into existence that are possibilities for some of these platforms. I hope that we, in fact, are more than a component of those. Although I think the Connect technology is certainly a candidate for a component for part of them. Like much of our progress in computing, we very often are building things for ourselves. And I think that, frankly, I think that no other group and leadership is more capable than taking on this charge of looking at these particular things that come. In fact, in the same notebook, the same day or the same period that I was at Microsoft working with Nathan, I outlined a robot, a telepresent robot that in fact is just coming into existence today. And at that time, Nathan said, "Gee, that's really far out." It didn't look very far out to me, but in fact, in my own fantasy factor, it's what I thought would be here 10 years ago is now one of these bodies that's there in 20 years in this time frame, and certainly will be prevalent within the next 2 decades. That those anthropomorphic, real physical robots will roam the earth, and I hope I hope their brain has a little bit of Microsoft software in them. Thank you.
All right, thank you, Gordon.
Yeah.
So we're going to take another short break. Let's resume at 4 o'clock. So about a 15-minute break.